Hi everyone, this is Michal, and today we'll go through a couple questions from the topic of performance from the Airhead Question Bank. So without any further ado, let's jump straight into the questions and we'll try to explain the principles behind them and all the answers. So the question number one asks us about um, during certification, demonstrating its one-engine inoperative gradient of climb in the approach phase. Choose the option that has the correct description of one of these prerequisites. Essentially, for all the questions that are asking us about prerequisites to determine certain speeds, climb gradients, or anything that has to do with about demonstrating during the certification process of aircraft's capabilities, you always have to think about most undesirable situations, meaning maximum landing mass, meaning unfavorable CGT, meaning the drag devices such as the gear being deployed. And of course, if this is a scenario during which you're doing a climb gradient from the approach phase, you will always have a full or takeoff thrust in the operable engine, as this will give you the most unfavorable yawing moments towards the dead engine. That is why here in this case, the landing gear retracted makes the most sense. However, remember that questions that ask about, for example, determination of minimum control speeds. So if you lose an engine during the takeoff, this will also be the same. So you'll have an operable nose wheel steering, you'll have the most unfavorable CG position, and maximum takeoff mass. And this question is correct. Now, question number two. Compared to a more forward position, a center of gravity close to but not beyond the aft limit. So these questions are quite common in a bank as well, and there are really only two types of these. So the CG is at the back of the aircraft or in the front compared to the neutral position. So what happens when the CG is forward? So if the CG is forward, that means that there is an arm pushing the nose, creating a nose down moment. And this nose down moment needs to be offset by a down force on the tail plane. So on the tail, if the force is down, that increases the effective weight, meaning this down force from the tail needs to be offset by an additional lift in order to stay level and to maintain a level flight. So the opposite is true when we have a CG near the aft. We have a nose up moment, meaning our tail is generating lift upwards in order to offset that down force created by the CG. In this case, if we have more downforce, so the CG is forward, our performance will be a bit worse. We'll need to burn more fuel, and so our range will decrease because we'll need to offset that additional required lift. Also, with the CG forward, we'll have a more stable aircraft. However, we will lose on the maneuverability. If the CG is backwards, we'll have a slightly increased range and increased performance. However, the aircraft will be less stable, but much more maneuverable. And knowing all this, going back to the question, if the CG is at the aft, that will decrease the longitudinal stability, it will improve range, and it will decrease the stalling speed. So this one is not correct. These questions are also quite popular in the mass and balance, so if you understand the principles today, it will definitely help with your future exams. Question number 3. When performing an increased V2 takeoff, our V1 speed will be increased. What related hazards should we pay most attention to? So V2 speed is our initial speed that we will climb out with in case of an engine failure after takeoff. Remember that the V2 speed is much lower than Vx, so this is not actually our best angle of climb speed. And this is why, for example, answer B, the climb gradient is reduced, is not correct, as higher V2 means we will have an increased climb gradient as our speed will be closer to Vx. Of course, increasing our V1 will mean that we will have a faster speed in case of a rejected takeoff. So we'll need more accelerated stop distance. However, this is something that we'll cross-check during the performance calculations to make sure that we are within the required brackets. The braking efficiency during a rejected takeoff will be reduced. Not necessarily the braking efficiency will be the same as in any case. However, because of the faster airspeeds, it will be the stop distance will be larger. The controllability limits, they refer to VMCG, so the minimum control speed on the ground, which is always before V1. And lastly, the stop distance may be compromised. I believe this answer makes the most sense out of all here, and that is also the correct answer. Now, question number 4. If the actual landing mass is known to be higher than planned. So if we have a larger landing mass, or generally a larger mass of an aircraft, a lot of things can happen and will happen. So if the mass is larger, we have more inertia. So the aircraft will not only accelerate slower, but will also decelerate slower, meaning in the case of both takeoff and landing, the distances required will be larger. Remember also that we will have a different stall speed. In case of a more mass, will require more lift to offset it, so our stall speed will also increase. And in this case, the landing will be unaffected. This is not true. The approach path will be steeper. No, not necessarily. We will be generating more lift, so it actually will be shallower because we have more weight on the aircraft. We'll need to generate more lift, meaning we will have a higher nose up attitude. And the landing distance will be longer. Yes, we have more inertia and we have a higher speed, meaning the landing distance will increase. Now, question number 5. If a jet airplane descends with constant Mach number, which speed limit will be exceeded? So, of course, we know or you should know the mnemonic chicken tikka masala, or eat chicken tikka masala, which refers to how the speeds correlate with altitude. So, if you have the three-finger rule, calibrated airspeed, true airspeed, and your Mach number, if your Mach number is constant and you're going down, that means both TAS and CAS will be increasing. Also remember that Mach number is a ratio. This is the ratio between the local speed of sound and the true airspeed. So as you descend lower, or if you're going lower, so you're descending, then the local speed of sound is slowly increasing. And this is something to remember. This is also why there is a point during the climb after takeoff when we switch from using the calibrated airspeed to the Mach number. So at certain points during the climb out, our main consideration begins to be the shock waves that can create a lot of drag and can inadvertently cause a high-speed stall. This is why we switch to Mach number. However, as we start descending, the air that's very thin at the higher altitudes becomes thicker and thicker, and this thickness of air, or dynamic pressure on top of the aircraft, is what creates forces. These forces have a limit, which are designated by the maximum operating airspeed, or further, the never exceed airspeed. This is why, as we are going lower, the high Mach numbers, due to a rising local speed of sound, are not that relevant anymore. And at this point, the most important consideration are the forces on the wings, so the dynamic pressure, so the calibrated airspeed. And of course, the airspeeds go first, we will reach the normal operation airspeed, VNO, then we will reach the maximum operating airspeed, VMO, and then we'll reach the VNE, never exceed, and VD lastly. And this is why I believe that the maximum operating airspeed is the first that we'll reach, and this is the first one that needs to be considered during a descent. And this is the correct answer again.